Hello and welcome everyone to MSC Software's webinar series. Today's topic is HDF5 for FEA, a standard for high performance and enterprise integration. The presenter for today's session is Ken Walker, who is the Senior Manager, and I'm your host, Bhumi Gadhia. I would like to kindly remind you to please fill out the polling questions. Your feedback is greatly appreciated. And at the end of the presentation, we will have 10 minutes for questions and answers. You can type your questions during the presentations in the Q&A panel, so we can answer them later. A recording of this webinar will be uploaded on our website in upcoming days. At this point, I will hand the presentation to Ken, and he will get started. So, Ken, you have the presentation.
Oops. Thank you, Bhumi. Good morning in Americas, good afternoon in Europe, and good evening in Asia. As Bhumi said, I'm going to be talking about HDF5 for FEA, and there's really two themes I want to dwell on. One is how HDF5 really enables high performance in MSC's applications that deal with results, and two, how for customers that do downstream calculations with results from their FEA runs can really integrate it into the enterprise relatively easily and using the toolkits that you're interested in, not just MSC developed toolkits. With that, I'm going to kick it off. Oops. Hello. So this is what I'm going to cover real quickly, just a slide or two, what HDF5 is and why we would pick it for an FEA implementation. Real quickly, I'm going to overview. There's now 4 applications in MSC that either create data or consume data from HDF5, and I'll talk just real briefly about those and when those came along and how they work. Then there's going to be a deep dive into the MSC Nastran HDF5 details, so I'll go through the whole evolution from the development through 2016, 17, 18, and 19 releases, and the capabilities are available in each one. I'll go through some performance examples we have that show the improvements inside of Patran, accessing different results file from MSC Nastran. Then the last third or so, I'm going to talk about the language and the software support and some customization capabilities. This is definitely not a deep dive into the programming part. I've got some slides that talk about resources that are available if you're interested in that towards the end. And then my last slide or two, I've just have additional references or resources that you can get from MSC if you want to continue to explore this. Just a quick reminder for those that are familiar with Hexagon Live, that's about 5 weeks out. It's in June in Las Vegas. There's still time to register. So if you have not been, I encourage you to go. If you've been, you know what kind of an exciting event that is. So the link to register there is at the bottom of this slide, hexagonlive.com, and we look forward to seeing you there. Oops. So real quickly, HDF5, what is it? Some people think it's somehow high definition or something like that. It stands for Hierarchical Data Format, HDF5, and it follows HDF4 and so on. It's developed by the HDF group. This is a spin out from a university work. It's a fairly mature software. It's been around for 20 years or more, and we're now using it. The little puzzle graphic there really just summarizes all the reasons people use HDF5 for large data. First of all, it's designed for big data. There's really not any limit. Obviously, there is eventually a limit, but in the practical world, there's really no limit to the amount of data you can work with. The metadata, or what's called the attributes, are tied in with the data, so it makes it much easier to describe what you've got, and that really gets into that easy sharing down in the bottom in terms of it's not hard to figure out what this data file is once you get used to how it works and how to look at it and all that. One of the nice things is you're not locked into any one programming language. I've got a slide later on that shows that it's written in C, but the number of codes you can use with it is pretty wide, and I don't think anyone's going to find that they can't access it with the code that they choose to use. And then in tying into the big data theme, there's some capabilities in terms of automatic compression, so it reduces the file size footprint, maybe at a small trade of I/O performance, but it's also got a concept of chunking, which allows you to work with data obviously if you have a terabyte file, you can't bring that all into memory, so you have to have a way to work with that file, and they call it chunking, which makes that better for these kinds of environments. And then the data format we use are fairly simple implementation, but the data format really supports any kind of data. So you can have tables like we've got, but you can add documents, you can add images, you can add graphs, just about any kind of data that you want to include in the format can be supported. So, for example, NASA manages petabytes of data. I used to have a slide, but they add so much data every day in their weather observations that I just talk about it in general, but they manage all their weather information historically in there, so they can manage huge amounts of data. And so what we do is kind of a bunny rabbit problem compared to that. So why large complex data sets? I probably touched on all the key themes, but it really is designed to manage any kind of data type and complexity, and FEA data certainly fits into that scenario. The nice thing that they're self-describing. If you've ever worked with FEA data, it can be one of those you don't quite know what you got when somebody hands you a model if you're not familiar with it. Well, these are self-describing. So between the architecture of the file, which I'll show in a little bit, and the schema, which describes each one of the components at a more detailed level if you don't really know what you're looking at. For example, like if you're used to working with modal data, it's easy to recognize the mode shapes, but if you're doing complex eigenvalues, it may not be so obvious what some of the data is. So it's all there in the XML files. And then the APIs, I show there that, like I said, it's written in C. There are bindings provided for C++, Fortran, and Java, and then there are extensions into Python and some other languages. So if there's a language you'd like to work in, I'll bet there's an interface to HDF5 for it. I think I've mentioned each of these other ones: high volume, complex data, every size and system. So MSC, we're running on Linux and Windows now, so that doesn't spread you out too much, but it can run in large HPC environments, and they have parallel I/O and all those kinds of things. So if you're working with real large data sets, you can do that. And then one of the nice things, HDF5 is fairly flexible, so as you want to evolve or do new things, I'm going to show an example of how we've done that at MSC. The evolution of HDF5 application. And then if you want to add new data models, so my last example actually shows some new data that gets calculated from existing FEA data, so you can see that. And then there are other actually file formats that use HDF5. I'm not really going to get into that, but you may be using a toolkit called Pandas or something else, and under the hood, or NetCDF, under the hood they're actually using HDF5 too, so sometimes you may be using it and not even realize it. So what makes HDF5 interesting for FEA in particular? Well, one thing that's nice, it's a compressed and binary file, so it's not something like for Nastran users to think of FO6 or whatever the text output is from FEA. Generally, you got to go look at something. This file is still human readable. Now, you don't open it with a text editor, but there's a tool called HDF View from the HDF group, and you can open that file, and it looks just like, I'd say, an Excel spreadsheet because it's tabular data, but it looks like a chart of data, and I've got a couple of examples later in the presentation that show exactly what you see in HDF View. So the need to print, if you will, a lot of data to a text file is reduced. And as I've alluded to, many applications can utilize it. So MSC Nastran can create data, and we're working on beta release right now of Marc that can also create HDF5 files. And then Patran and Apex right now can access or consume that data and use it. And of course, your own programs could do the same thing. And you can create your own data. So if you wanted to calculate some additional value, you can calculate that and put it into your own containers. And we actually have customers that are already using it. So some of our customers are actually in front of us when we were doing this. And we're pretty excited to hear that we are using HDF5 because it ties right into what they're already doing. So specifically for Nastran, this might look familiar. Now, this is an amalgamation of a lot of different processes, so I don't think any customer actually does what this picture looks like. But, you know, everybody writes an FO6, and they read that and may or may not pull data out of it. I have some customers that create punch files because they're pretty easy to handle. They're nicely formatted, so if you want to pull them into Excel or do some kind of report tool, it's already nice and it's organized, you know, as opposed to trying to parse an FO6, which can be a little bit of a headache depending on the data you're dealing with. So if you want to do your post-processing, Patran can post-process the XDB or the output too. I didn't want to make this too complicated, but you need that file for attachment. except if you're running the nonlinear capabilities or contact and solution 101. Those are really in the master DBAL, so you need a different data entity for doing that in Patran. And then there are a lot of customers that have internal programs that either read the OP2 or the XDB or one of those files. I just picked that one just to show it. So you can land up with a lot of data artifacts, right? You got one input file, let's say, and you can land up with a text file and an XDB and a master DBAL. All of a sudden you have a whole bunch of artifacts to keep track of as a follow-up. And if you think about HDF5, that same process, really just two output files in FO6 that would have errors and warnings and maybe some small modicum of text that you need output, maybe some key variables that you want to have them review. But then everything else, you have the HDF5 file. It's human readable, as I said, with the HDF View tool. If you want to go pull some data out that's in spreadsheet format, columns and rows, you can do that when you're in HDF View. You can highlight and extract the data and copy it out. Or if you want to write out a whole table, you can just extract that whole table and write it out. So there's no need to go start punching a bunch of separate files and figuring out what's in them. Patran can attach that file. So 2017 on, we can just attach that file and do post-processing. And it supports all the nonlinear capabilities. So even if you're running Solution 400 or touching contact in 101, not a problem. All that data is there. And then if you have an internal program, I'll talk about it, like I said, at the end, the programmatic access. So you can do the same thing and hook it up to whatever you'd like to hook up to in your enterprise. So we did the initial implementation in 2016 with MSC Nastran, and there's been a number of enhancements in 2017, 18, and 19, and I'll highlight those a little bit later. The default is that both records from the input file and the results are saved together, so you have a single monolithic file that describes both the input and the output, so there's no figuring out, hey, is this the output from this input file? It's always tied together. And then the results post-processing has been supported in Patran since 2017, and then, of course, with the 2018 and 2019 releases, we updated it to be able to manage the additional results that were added in the matching Nastran releases. Shown there is just a real simple view. So I mentioned HDF View a couple times, and so you know what I'm talking about. This is just a snapshot. I've got a video a little bit later. This just shows the basic layout of a file. So you can go in and you can tell underneath input, it looks like folders and files. Under input is where all the input data is stored, coordinate systems, elements. You don't need PhD and HDF5 to figure out what these things are. They're named with words that make sense, at least in English, for those that are working with the file. And underneath the results, you see the same thing. If you want some kind of element result, that would be under elemental. And if you want some nodal quantity like an SPC or displacement, it would be under nodal. And you just keep opening them. And when you get to a data set, you can look at the data. This shows the input data. Node grid is the coordinates and the other data associated with each grid. So you can see the ID of the grid. You can see CP is the same as on the Nastran bulk data card. It's the coordinate system for position. CD is the coordinate system for the displacement field. You can see PS and superelement ID and domain ID. So those are used for whether you're using a superelement or when we do multi-step analysis, whether or not it's included in a particular domain. But the first 3 or 4 fields should look pretty recognizable to a Nastran user. Oops. And with the most recent release of MSC Apex called Iberian Lynx, it came out in January, right at the first of the year, and it can now access in a workflow the HDF5 file that comes from an exported file. So if you think of the workflow, start in Apex, either bring it in CAD or PDF, do some kind of modeling task, set up an analysis, do the analysis, and instead of running with the solver, you run it by exporting the BDF, run it with Nastran, and you get an HDF5 file from that. You can attach that matching file and do your post-processing inside of Apex, whatever kind of modeling you want. And you know, there's tools to extract a common delimited file. Say you create a table. And the 2 images there just show the 2 results. So an image for a model using the HDF5 file in Apex. And then, you know, whether this is just a checked image, but whether you had some of the downstream process that still required Patran or you wanted to do something, you could bring that same file in and you can see the results are are identical, the same numbers. I mean, there really should be. There's no reason why they would be different in Patran and Apex, but you can see the numbers are the same when we look at the grid point values there, and they're just compared. So that's just came out. It's what, 5 months old, and I certainly know a couple of my customers are interested in that because they use Nastran as a part of their process, and so now they can do that with Apex cleanly. And coming soon, so Marc 2019 is in beta right now, and this is the first release that Marc can create HDF5 output. So the initial implementation is going to have a schema that's compatible with the Nastran schema format, and it's going to support the elements you see there, the linear continuum elements, and output a subset of results, but a pretty significant subset when you think about typical workflows, displacements, forces, reaction forces, the stresses and the strains from the elements. And there's just a couple of keywords that are used to control that, specifying which results you want with the HDF post and which HDF post flag you want to use for a particular load case. So pretty straightforward. Like I said, it is in beta, so if you're interested, go to the MSC beta sign-up link and you can do that, and then look for the release later this year. This just compares the results in the same way, no surprise. When we look at the H5 results in Patran, you can compare those to the T16 results in, doing it in Mentat, this sort of old-fashioned way. You see the same kind of numbers there. I don't know if you can read them, but they're basically the same number because, of course, they are the same number. They're just being written in a different format. And so as customers have started to tinker with this, I hate to say the word play, right? We come to work, we don't come to play. But as people are tinkering with it, exploring it, testing out what does HDF5 mean, gotten a couple of quotes. One user was just trying to write some real simple integrations. It wasn't a big project, but he needed to be able to go and pull the same set of data from a bunch of different load cases. And so he wrote a real simple Python script to go do that. And this was a guy that had never seen HDF5 before, hadn't done a lot in Python before, and he was able to go off and create that really with no help from me. I gave him some directions in terms of what to go look at, but did it on his own. And he was really, this was his comment back, was it was so easy to interrogate the results. And of course, he noticed the performance improvements when he attached the results files to Patran and how quickly he was able to pull the stuff out rather than trying to write a FO6 parser or something like that. So much easier to work with the structured data. And then we had another customer that recently, rather than using an FO6 tool, they wanted to be able to do their loads processing and made the decision that they would do a test project using HDF5. And again, brand new to the technology, brand new to the toolkit. In their very first project, they saved 6 man days. So, it wasn't 100% savings, right? It wasn't a 12-day project they cut in half or something. But 6 man days, when you start working out the burden rate of 8 hours a day, 50 hours, it turns into real money pretty fast on the first application. So when MSC started down this journey, there was some development goals, and we were exploring what happens if we put HDF5 export into Nastran, and what happens when we put HDF5 access or import into Patran. And really the first thing was, let's just make this easy for customers to use. Anybody that's worked with MSC Access to read XDB knows that working with external files are a little bit of a mystery because they're binary and you can't see anything. And so you have a mistake and you write a program, you got to write another program to go probe it. So with this, it's much easier to explore, and quite frankly, with HDF View, you almost never need to look at the schema anymore. I don't ever look at it unless I'm in an area where I don't understand what the data is and I need some more information. So it's really easy to understand the data and the data architecture. With Patran, the goal really was to improve scalability. So for those that build really big models, and I'll show some data, sometimes you'll see performance bottlenecks accessing or plotting the data. And so the goal was, this is really an I/O issue. It's not like a solver, right? With a solver, usually it's CPU or memory or something that causes a problem in the solution. But with data access, it's really the I/O and the amount of data you have to access impacts the performance. So the goal was to keep our performance for small and mid-sized models, so we have good performance there, but to significantly improve the performance for very large models where, quite frankly, users were waiting on the application to access the data. And we were able to do that through the random I/O access capability. So HDF5 has the ability to go find, if you want to go find subcase 27 or something, you can find that very quickly and not have to dig through all, 1 through 26 to get to that. So it certainly improves that. And that's what our prototypes demonstrated, was that when we use compressed format, the database was smaller than the OP2 file. And in some ways, that's a little hard to compare, because the HDF5 file is always written in an I8, so it's always in the long or high precision format, as opposed to OP2 may or may not be. So even with the high precision, it's always smaller. Uncompressed, not always true, but that's really just a decision you want to make. We see faster access, attach times, and then the plot times. And I've got some charts to show that. So you don't have to take my word for it. I'll show you some examples where those numbers are borne out. When we did the implementation, the input and the output data structures, you already saw a preview of that. We write all those by default into the HDF5 file. Over time, some customers wanted to be able to separate that, so we adjusted that a little bit. And I'll show you how you can manage that when we go through the particulars of writing the file. The data is laid out in a fairly logical hierarchical structure, so I showed you that, and I'm going to go through another video again, but it's very simply in HDF5 language. Groups are like folders that organize the data, and then there's the words are used a little bit interchangeably, tables or data sets, but there's 2D tables inside there that actually have the data, and you can see those in each of the columns as names. So everything has a name. You're not just working off of indices or something like that. Everything's pretty straightforward. And as I've mentioned, it's all straight HDF5 API, so you can pick whatever you'd like to use and use the software you'd like to use to go do that. And the process is really, it's the same. It's really just the coding language, but the way you would go get that is you go find the group and the table and read the data. And we provide 11 or 12 examples in 3 different languages. So there's C++, Python, and Java examples. So if you want to see how to do that, we give you some simple ones to go do that. And the schema is delivered. And I've mentioned here it's in the doc directory. It's also in the release guide directory. So we deliver the current version plus all the previous versions. So if you have Nastran 2019 installed and for some reason you need to go see the 2017 schema, that's also delivered in an older folder that keeps that documented. And if you want to find them, basically just go to your Nastran 2019 and just search for data type XML or data type HTML and you'll find it. But I've got the directories there just in case. So we've been doing this since 2016. The initial rollout included a number of solution sequences. I think that's 10. So you can see all the usual ones: statics, modes, buckling, complex eigenvalues, the frequency response and transient response in dynamics, and support for design optimization and multidiscipline analysis and nonlinear sequences in 400. And really, to get an HDF5 file, not much more than just adding a single line model parameter HDF5, and then there's in the initial rollout 3 options that were there. The default is we don't write it right now, but it's pretty easy to add it in if you have an existing model. And then in 2017, there were a number of enhancements. So we added a summary table for complex eigenvalues. So complex eigenvalues are already written. We added a summary table, added some composites output for linear, additional enhancement for optimization for design sensitivity. I'm not going to go through all the bullets, but highlight some of the key ones. And then there were some new features. So we reorganized how vector data is written. So vectors could be displacements or forces. I guess those are the 2 big ones. Well, accelerations and velocities when you're doing dynamics. And the original format was simpler in terms of the way it was accessed if you wanted a vector. But if you wanted a component of a vector, quite frankly, it was a little bit of a headache. So we made a change that overall is a change for the better. Obviously, change is always a little bit of a challenge if you're trying to write a program. But in general, I think most people that work with vector data will find the newer format to be better. Some customers really aren't interested in rotational output, so we've got an option now that if you don't want the rotational components, you can turn those off. And turn off whether or not we just write the input and output data or just the output data. And for those doing nonlinear analysis, there's an option to write the intermediate results if you want those or not. 2018, you can see it continue to extend it. So some new optimization outputs for topometry and topology variables and the response data. The wet faces associated with acoustic analysis. I didn't mention this, monitor points in the previous version, and then we extended that to monitor points for Solution 200 in the AE set. So for those that do a lot of shear moment calculations that fix points down their structure, monitor points are pretty handy when we do that. And an interesting one for those that want to get matrices, there's the capability to output matrix data. The default is the matrix output is in the modal space, but there's options to flag that. And a few slides from now, I'm going to show some DMAP calls that you can use to manage that matrix output. And we've already gotten some questions on the forums on that, so I know there's some interest there. A couple of nice things. In the previous two versions, the HDF5 file was always just named jobname.h5. So if you want to assign it to a different file, you can. And we've now provided versioning, so if you run it over and over, you get new HDF5 files, so that's handy. And then, as I mentioned, if you want to split out your input data for that particular run to a separate file, there's an MDL parameter that'll handle that for you. And with the most recent release, 2019, we've added support for the aerodynamic analyses 144, 145, and 146, and modal effective mass. We added modules in 2018, and there's additional module support, although the 2018 output includes modules data, and it includes the domain flag. So if you're running 2018 and you're using modules, those are already marked. There's just some extensions for that. And then a few other things, too, in terms of like the contact checks. That's a new feature in Nastran, and so that feature migrated into HDF5. And it doesn't really say the global grid point force balance, but that was also put in, and that's also a part of HDF5. So if you have an existing model and you want to start looking at this, there's not much more than just adding this model param HDF5 and a number. The default is if you don't input it in -1, so we don't write it. You can see the other values there with or without compression, and then do you want it without the input data if you're running a more current version, compressed or uncompressed. And that's really all that's required. You get it. And one of the nice things for those that are looking at this but don't want to migrate off, you've got some process that uses XDB or some process that uses OP2 or something. If you put in the param post value, you can get output 2 or XDB and HDF5. So it provides a nice transition method that you can go off and explore both paths as you're going. So I mentioned Patran performance. What do you get out of this? So in the linear world, there are improvements, but it was already pretty fast, so maybe not as much. But if you compare the H5 compressed column to the OP2 column, in every case you'll see the file is smaller. In some cases it's a lot smaller. For example, in nonlinear, it's a factor of almost 3, right? 22 down to 8. In the buckling analysis, 2.9 down to 1.8 is not so much, but linear statics is about half. In statics, the attach time is pretty fast, and it stays fast. Where it's interesting is even creating a von Mises stress plot, if you compare it to XDB, is 3 seconds to 10 seconds isn't a lot, but if you're going to create 50 of those, all of a sudden 3 seconds times 50 turns into real numbers. But if you look at the nonlinear, the buckling analysis, because of the number of cases, so 500 modes represents 500 cases that have to be indexed, and maybe 50 increments for nonlinear isn't big, but all of that indexing, there's a performance penalty paid on the XDB and the OP2 that H5 is much, much faster, both to attach and to create the plots. And I show both compressed and uncompressed because there's kind of a trade-off. I use compressed, my file size is smaller, but I have to run the compression algorithm as I go in and out, so there's a little bit of performance, so it's really a trade-off in terms of disk space consumed versus file I/O. There is an option to, if you're going to work with it a lot, you could save it in an uncompressed format because you get a little bit better performance, and then when you want to archive it, there's a way to actually not zip it, but actually compress it internally, so the HDF5 file is still usable in that format, but it manages the compressing internally. So just a trade-off there. This is another example that's not one that I put together, but one of the AEs that works for us in FEA, and it summarizes a big model, solution 111, lots of nodes, lots of frequencies, and you can just compare the charts. So the gray lines are with the XDB, and the green chart shows performance with OP2, and then the last two are whether you use compressed or uncompressed HDF5. So in this case, the HDF5 file is not smaller. It's on the same order when you use compressed as the other data values. But if you look at the database size in Patran, it stays small. And if you look at the I/O in the fourth from the left or second from the right, you can see the hand-in-hand relationship of amount of I/O in gigabytes versus performance. It's it's just amazing, right? You're going from seconds that are measured in hundreds task times and plotting times down to 7 or 4 seconds. So pretty darn fast. So for those working in the dynamics world, this can be a pretty big improvement. So I mentioned language support. So everybody likes to do their downstream applications in their favorite language. And, in the past, if you were using XDB, you were locked into C and Fortran. And if you wanted to do something else, you had to figure out how to wrap a new programming language around that. So HDF5 is written in C. So that, at the end of the day, if you dug down to the original source code, that is what it's written in. But the HDF5 group provides wrappers. So if you prefer to work in C++ or Fortran 90 or F2003 or in Java, those wrappers are also available from the HDF group, and they're all built out for you. Python's a big thing in the data science world these days, especially with extensions that I've got listed there. And so there are 2. Our examples in Python are delivered using the PyTables module. There's another one called H5Py, which is for those especially that work with NumPy. It is a very natural mapping of H5Py dataset table access into NumPy array. So it's pretty straightforward. And there's another toolkit called Pandas that some people uses data frames, and it's built on top of PyTable. So a lot of choices in the Python world. Sometimes dealing with that can be a headache, but if you're using a package manager, so Anaconda or the pip package manager, pretty straightforward to get those installed and running together. And there's also application plugins. So for those using ParaView or Visit, there's some plugins that will allow you to work with HDF5 inside those applications. And then there are third-party software, so we're not the only ones jumping on this. MATLAB has a tool to go off and read that, and I'm going to show an example of that in a second. Mathematica and Insight have ability to read that file, and the Intel Array Visualizer and Array Viewer. So there's a number of tools that can read this data in addition to our tools. So those release guides examples, I've got the specifics on it in a slide or two, but this is out of actually the release guide, so save you having to go read that. But if you want to know which versions are required and all that. So the Python examples use PyTables. So you can use H5Py. There's nothing wrong with that, but you'll have to rework the examples a little bit because it works a little bit differently. You have to find the comparable call. But all the PyTables examples work straight up as they are. And so you have to install those, but it's pretty straightforward. If you don't have Python, you install Python and use your package manager and go install. PyTables will actually install NumPy for you, so there's really not any extra work. It takes care of that for you. If you're running C or C++, this is a list of the requirements here. This is out of the 2016 guide. I have to be honest, I did not go back and check if we've updated those, but later versions should also work too. There's no real tie-in to particular version. And this is the version that we're using for HDF5 now, but we've now are migrating to 1.10. So later versions of Nastran will be higher versions of the HDF5. I mentioned DMAP support. Most customers are probably not going to be interested in the first 6 of these. The last one's the one that I mentioned earlier. So there's the ability now in 2018 to output matrices to the HDF5 file. And the default is you get the modal matrices, but if you wanted something else, like you want a stiffness matrix or some other matrix that's not written by default, you can request that, and then you use this call here, this CRDB MTX, create the database for the matrices, and in that call you can change which matrix you want to write out and do that inside of the DMAP, and then it's written into HDF5, and once you have access to that, you can either just cut and paste the table out if you need it, or if you want to go write it programmatically, you can. So pretty straightforward. It's actually come up several times with customers just since it was released. So I mentioned that in detail because I know there's some interest in that. And then I also mentioned MATLAB. So a lot of users, MATLAB is something everybody seems to learn in college these days. And so if you are familiar with MATLAB and like to work with your data there, you can see real simple here. An example, the first one is where we're just reading the H5 file, specifically the example I showed you earlier. So the file description and the path Nastran input node grid was the example I showed you, which gives you the grid coordinates for all the grids, well, and all the other data too. So that's that example. The second one further down actually accesses the whole file, and it just gets the info related to it. So it shows the path, where the file is stored, the name, the number of groups, and things like that. So just a couple of examples working with MATLAB. I'm not a MATLAB user, so I can't go into details, but once you have the data in, I understand it's pretty straightforward to work with. Now, this webinar is not intended to teach you all everything you need to know about programmatically working with HDF5, but it is intended to show you that working with it is pretty straightforward. So just understanding the data model. So even if you open it with HDF View, you know what you're looking at. So we call it self-describing, and it just says that the hierarchy describes the data model. When you look at it, the names are pretty straightforward, and it should be self-explanatory, at least for the more common ones. Like I said, if you've never done complex eigenvalues and you get into a complex eigenvalue solution, it may not be obvious, but for the more obvious ones, it is. And this is just a repeat of what I showed earlier, that hey, if I went in and looked at the Nastran input node grid table, you see a row, and each row has a grid ID and then CP for the coordinate frame used for the position. Then X is the values of the coordinates, so you can see those coordinate values there, and they just go on and on and on for however many rows there are. And we reference each row, and then once we get to a row, we just reference which column we want. So row is a variable, but row quote-unquote ID would get us the ID, and row quote-unquote X would get us a vector with the X, Y, Z values for the coordinates and so on. And CP and so on will get the other values. And so yeah, if you start working with HDF5 just in trying to explore it and see what it does, I would recommend that the first thing you do, of course, are Nastran run, and then the second thing you do is you get this HDF View and install it. It's a Java browser, so you can just open it and look in the file, and if you add a shortcut, you can actually just double click on it. That goes beyond what I can cover today, but pretty easy to do. You go in and look. I'm going to have a video here in a sec that shows what's laid out. But if you wanted to go get the data, you could just go pick and highlight something and copy and paste it. If you want a whole data set, there's a tool on the file menu. It says export data set, and you could write the whole data set out. So you probably wouldn't write out the whole data set of the grid or the quad connectivity here, but you might want to write out all like your SPC forces, right? So go get those out and put those into an Excel file or something like that. And you can open it read-only. So unlike F06, which is a little hard to lock down, it's a text file, and there's always the risk that it can be damaged. You can lock these down to be read-only so that no changes occur. And I've got the link there just so if you want to go get HDF View, instead of having to do a Google search, you can just use that link. But it is as easy as, you know, Google search for HDF5 View. So let's get this video going here. He said, Well, this was working earlier. Shoot. Well, I'm sorry. I don't know why that's not playing this morning, but it's not happy with me. We'll make sure we get that fixed. But this would show going through the, let me get out of here, maybe. Okay, here we go. So yeah, so there's a view. This is a little video showing a user going through, and we're starting off. The first example is just going through and looking at the grid cards that I've been talking about before. If you wanted to see the connectivity, there's the elements, and each of the element types is shown. So this shows the grids that form the hex elements. So it could be 8 or 20 node. Now the user's going in to look at some results, and here's the displacements for the nodes, and you can see the value column there that shows the coordinates. It's a vector quantity here, and the domain ID references the subcase, so to speak. And if I wanted to go look at the stresses for those hex elements, the same thing. So you see the element ID, the type of stress. So Gauss says it's at the Gauss points. And you can see the individual components, X, Y, Z, and the shears were over there for before we scrolled off. So that's that. Okay, so good. So a little nomenclature, because it helps to have a few words when you're talking about this. Again, this is not a deep dive, but it's helpful when you see some discussion about how HDF5 works. So the concept is that there's groups and data sets or tables. Data set's a generic term. The specific type we have is all of our data sets are tables, but there could be other things. And it's really, a group represents a folder, if you think, or a directory in the Linux world. And then the data sets is the actual data as you saw there before. And all of our data sets are tables, pretty straightforward to look at. And again, I've mentioned the schema. I mentioned it a bunch of times because you hate to be on a slide and say, hey, where was that schema thing? I have to scroll around. So it just mentions it there. But again, you can just find those by searching for data type, XML, or data type, HTML, and they'll show up inside of the Nastran directory. Quite frankly, I just go to HDF View now. I rarely look at the schema anymore. It's just not something that's required once you have the concept. And so this is just sort of a very quick Rosetta Stone to the input model and what's there. So that this is the input data. This just represents, if you will, what your bulk data file has in it. It's not a 100% representation, not every parameter control, but all the model data. So all the elements, all the nodes, all the loads, all the properties, most of the case control is in there. The domain definition. So domain is kind of a funny thing because it's not a Nastran word. Domains are really, when you do a solution, if you're doing linear statics, each of the subcases would be a domain, right? It doesn't matter whether they're one. Subcase, the first subcase is domain 1, the second subcase is domain 2, and so on. If you're doing frequency response, modal analysis, you might request 100 eigenvalues, so each one of those becomes a domain. So it's the way we manage different results at different points. If you're doing a time solution, each time point becomes a domain. And if you're doing solution 400, where you might have things that are mixed, you might have like a preload nonlinear analysis. Each one of those is a domain, and then the modal analysis that follows because you did pre-stress would be a domain. So that's really where you just manage where the results are. So that's in there. Same way then in results, you see here, so a separate folder's open. There's a set of domains that show the results domains and the different kinds of results. And there are different tables. The key thing here is the results from a C-bush element are fundamentally different than the results from a quad 4, and those are fundamentally different from a continuum solid element. So each of the element types gets a different table to keep the data organization straightforward. So when you have different results types, you're going to see different tables because they have different results in them, and the organization of the table is different. Rather than trying to make the table generic and you got to go figure out what you got, the tables are specific and it's relatively straightforward. In the same way under nodal, you see displacement, but SPC forces would be the same way. The grid point force balance would be down there. And then this is not something the average user would use, but if you're writing an interface and you want to go pull the results, I'm going to mention it just real briefly. So there's an index set of groups and data sets, and these indices really just provide a fast index that says, hey, if I want to go to get the result for a particular domain for the bush elements, or I want to go get the displacement results for a particular subcase, these indices do that very quickly. They tell you the starting row and the number of rows you can read. So rather than having to go in and pull all the data and look at the domains, these are a real quick way. So I mentioned those mostly for people doing programmatic interfaces. If you're not writing a program, you'll never look at the indices out. But it is a handy way to really write fast code. And that's one of the things that Patran leverages to get the speed up. But as I said, there's some code examples delivered. You don't have to start with a blank screen. Go grab one of these and look at them. They're simple examples. And the nice thing about simple examples is you see how to open the file, you see how to read a table, you see how the data works and how you might write it out. And then from there, of course, you would build it on if you wanted to do something more sophisticated. So there's 4 of them in Python. There's 5 or 6 in C++, and there's 1 in Java. And so, for example, you can compare reading nodal results is the first example in Python, and it's the 4th example in C, and then there's 1 in Java. So if you want to compare the capabilities, you can do that. And there's 1 that's exactly identical. So example number 8, there's sort of an 8A and an 8B to go write displacements and hex stress data. And you can see it in Python or C++. So they're all there, and they're in the same delivery directory with all the other HDF5 information. And that's one location. You can also find it when you go search and look in the release guide for each of the deliveries. You'll see them there too. We also have links for those that want to go get them off the SimCompanion website, and I've got that on the resources page. So I'm going to summarize the last 3 here. I'm getting close to my ending time. I've done 3 customizations. I'm just going to mention those real briefly, give an idea what you can do with them. So one is a complex von Mises stress. As you know, that's not a simple calculation. So a paper was presented a number of years ago at the MSC conference called the Charon method. And one of our team in Europe developed this, and I really just took it and extended it to work in a more generic way and work with NumPy arrays and sort of improve the overall output so that we could have common delimited summaries and create a Patran neutral file. So if you want to be able to go off and bring those results in, you could go look at that. And this next slide just shows. So here's on the top the HDF5 output, and what you're seeing is the results for a hex element, really just one domain. So if I think this had 100 frequencies in the analysis, you'd have to go through 100 lines for one element, then 100 lines for another element, and so on, and do the calculations, and then go figure those out. And so what this does is it does all the complex stress calculations, finds the max, and it says for subcase 1, which frequency had the maximum complex von Mises and which the phase angle for that. Now, interestingly, most of these occurred at frequency 80. There's one exception where it occurred at frequency 460. But sometimes you would see different parts of the structure respond differently. You would see different frequencies, so you can get that data out. And then there's a matching Patran neutral file you can use and import and go plot those same things if you wanted to look in Patran. I mentioned modules. They were introduced in Nastran 2018, and if you have unique IDs across the model, Patran can post-process that just like any kind of results. But the advantage of modules was that 3 users could each build a model starting with grid 1 and element 1, and they could merge them in modules, sort of like part superelements, but without reduction, I guess is a way to describe that. And of course, if you have 3 nodes that all reference grid ID 1, and you have 3 elements that reference element 1 and 3 properties, that doesn't work in the Patran world. You have to break those apart, which for post-processing, probably separate users created them. And so this tool does the same thing. It takes the results and splits up the module results into 3 different or 4 different, however many modules there are associated with the domains. And I mentioned indexing. That was kind of a trick that tripped me up. Initially, I did it and it didn't work, and it's because I didn't have the indices data for Patran. So I create all the indices too. So now it's not just the data split up, but it works. So you can think of it this way. This was 4 examples. You get an HDF5 file and you want to split it out into the modules. Whether because of IDs or individual users are working on different parts of the structure, you can break those out and work with them, and it takes care of everything for you. Then the last one's one, we get a lot of questions from customers about doing buckling, and it gets complicated when they're trying to figure out what the global and the local modes are. So we actually had a paper presented back in the 2002 user conference. It showed a technique using statistics to go out and help identify which modes might be global modes versus local modes. And it's a nice tool. It works really well, but you have to know the DMAP alter exists, and you have to put the DMAP alter in your Nastran run. And then after you get done, I'll show you an example of the output. The output's, it's just dense data. It's hard to go through and find the maximums. And if you want to change, it's got a bunch of input options. If you want to change the input options, you got to rerun it, because the only way to rerun the DMAP is to rerun the analysis. And as you know, if you're running a lot of asking and requesting a lot of eigenvectors, you're paying more for the buckling calculation than you are for the DMAP calculation. So I thought this is something that's really a good idea, that you do your buckling analysis once, and then we can just do the post-processing. So this just shows the example DMAP output that's printed to the F06. And I'm not going to get into the mathematics, but there's the means calculated, the standard deviations calculated for the mode, and then something called a weighted standard deviation, which tends to really highlight the global response. And this just shows, first of all, there were 500 modes in this analysis. So that table you see is about 1/3 of the table, and it's repeated 3 times because you have the mean and then the standard deviation and the weighted standard deviation. And so, finding that 1.23 e to the -1, that's the highest responding mode in that table. I'm not saying you can't do it. I'm just saying it can be a little challenging. But with the Python output, the same output's created, but in a tabular form, along with the top 10 where the values are sorted. And of course, once you have it in a spreadsheet, it's really easy to sort it. So figuring out which mode is the one that responds the highest is much easier for and of course, then finding the second highest mode and the third highest is much easier to do with this than it would be through the DMAP. So it's no numerical or any issues with the DMAP. It's just the output's a little bit hard to work with, and the Python's, I think, a little bit easier to look at a CSV file, and it's easier to work with downstream. So that really is the end of my presentation. These are the resources We'll have to make the slides available so you can go get those. But those are links to the different release guide examples and a GUI example for Python. And then I've had 2 Sim Academy sessions, which are deeper dives. I'd say this is about half of what I present in that first Sim Academy session. And then the second one is definitely a deep dive. It's got coding and Python and how the data model works. So for people that really want to work with that, I suggest they go look at that. And then for those that are really interested, I've developed some training modules that sort of begin where Sim Academy is, but goes into a much deeper example and extends it into NumPy and a whole bunch of things. So if you really want to deep dive into doing some work with Python and HDF5, the e-learning is available on the MSC e-learning site. And that really brings me to the end. We've covered all these things.